Hi, I am Daniel Ditan, a third-year mechanical engineering student from Section 3A. So today, we'll solve a problem with the use of the moment area theorems with statically indeterminate beams. But first, let us recall what are statically indeterminate beams. In regards to beams, if the reaction force can't be determined using equilibrium equations only, other methods have to be used, and the structure is said to be statically indeterminate. For some beam configurations, here we can see that in this beam, we have 4 reaction forces but only 3 equilibrium equations, and thus, we can use the moment area theorem to solve this beam by determining the reactions at the supports. From the Book of Mechanics of Materials, 4th edition by Beer and Johnston, we have the problem 9.129. For the beam and loading shown, determine A, the slope at point A, B, the deflection at point D, use E is equal to 200 GPa. Here are the steps in solving the problem. Number 1, draw free body diagram. Number 2, determine reaction forces at the beam supports. Number 3, determine and draw shear and bending moment or M over EI diagrams. Number 4, solve moment area by parts. Number 5, draw a deflection diagram. And lastly, number 6, solve the slope and deflection using the moment area method. For the given, we have the E or Young's modulus, which is 200 gigapascal or 200 times 10 raised to 9 pascal. From Appendix C, properties of rolled steel shapes, the moment of inertia or I of the beam is 71.1 times 10 raised to 6 quartic millimeter or 71.1 times 10 raised to negative 6 quartic meter. The required of the problem is A, the slope at point A, and B, the deflection at point D. For the solution, first, here is the free body diagram from the given problem. Solving EI is equal to 14.22 times 10 raised to 6 Newton meter squared or 14,220 kilonewton meter squared. Next, using the equilibrium equations, we can solve the reaction forces at point A and point B. From the given, equation 1 is RA plus RB is equal to 40 plus 20, which is equal to 60 kilonewton. For the second equation, we'll use equilibrium of the moment at point B. Summation of moment at B is equal to 0, which is equal to negative RA times 6 plus 40 times 4.5 plus 20 times 3. Moment at A is negative since it is clockwise. Substituting the known values in the second equation, we can solve RA, which is equal to 40 kilonewton. Substituting the value of RA to the first equation, RB is then equal to 20 kilonewton. The reaction forces at the beam supports can then be used to determine and draw the shear and bending moment diagram of the problem. Here is the shear stress diagram corresponding to the forces and reaction forces acting on the beam. Using shear stress diagram, we can then solve the moment at point C and point D in the diagram. At point C, M is equal to 40 times 1.5, which is equal to 60 kilonewton meter. On the other hand, at point D, M is equal to 40 times 3 minus 40 times 1.5, which is also equal to 60 kilonewton meter. With this, we can draw the bending moment diagram as shown in the screen. These values can then be used to solve the moment area at each part of the beam. From the bending moment diagram, 60 over EI is the height of the shapes formed. Substituting these values with x as the base, we can then solve area of triangle 1, which is equal to 45 over EI, area of rectangle 2, which is equal to 90 over EI, and area of triangle 3, which is also equal to 90 over EI. Next, here is the deflection diagram of the beam. Calculating the tangential deviation of point B with respect to A, substituting the area of each part and the horizontal distance between the centers of the shapes to each point, TBA is equal to 742.5 over EI meters. Then, the tangential deviation of point D with respect to A is equal to 157.5 over EI meters. To calculate the slope at point A, we can use the formula theta A is equal to TBA divided by L. Substituting the values to the formula, theta A or slope at point A is equal to 8.7 times 10 raised to negative 3 rad clockwise. To calculate the deflection at point D, we can use the formula YD is equal to FE minus DE. From the deflection diagram, the equation can be written as YD is equal to TDA minus XD over L times TBA. Substituting the values to the derived equation, YD or the deflection at point D is equal to negative 15.03 times 10 raised to negative 3 meters or 15.03 millimeters downwards. And that's all for today. Thank you for watching.